A very good morning. In the interest of time, we'll get started. My name is Arun Tangirala. I'm a faculty here at the Department of Chemical Engineering and a core member of the Center for Complex Systems and Dynamics. So it's a pleasure to welcome you back after the break. We have 3 talks scheduled in this session. The first speaker, Dr. Kazuyuki Aihara, I hope I've pronounced the name correctly, is joining us online. He's unfortunately not able to make it in person. Dr. Aihara is from the University of Tokyo. And then the remaining 2 speakers are here and will deliver their talks in person. So over to you, Dr. Aihara, in the interest of time. And just to let you know, let the speakers know, we have 35 minutes overall for each talk. I request each speaker to leave some time or some room for discussion, at least about 5 to 7 minutes. Thank you.
Okay, thank you very much, Mr. Chairman. Can you hear me?
Yes, we can hear you.
Okay, thank you very much.
Thank you.
So first of all, I'd like to thank the organizers for inviting me to this wonderful conference. And I'm very much sorry that I cannot attend in person because this summer there are too many conferences and symposium in Tokyo. So it's very much pity that I cannot attend in person. Okay. Today I talk on the prediction and its applications with high dimensional data observed from complex systems. And we have been working on the analysis of a complex system. So on one hand, we are making the mathematical methodology to analyze the data, high dimensional data. And simultaneously, we are applying such methodology to real world systems like the blast furnace, integrated circuit, infrastructure system, brain and neuron, diseases, and infectious disease, and the pandemics. And for the analysis of the complex system in general, we have developed a theoretical platform composed of the 3 theoretical fields. One is the complex system control theory by fusion of dynamical system theory in mathematics and control theory in engineering to control dynamics. Second is complex network theory to optimize network structure. And third is nonlinear data analysis or data-driven modeling to analyze the observed big data for the application like the prediction. Okay. And today I talk mainly on these topics, but because I didn't introduce this one. Okay. So this is a fusion of the dynamical bifurcation analysis and robust control. Okay. And this is the example of the genetic oscillator called replicator. And if we are given the equation, then this is the parameter space, and we can calculate the bifurcation set. In this case, Hopf bifurcation. And in the blue region, equilibrium point is stable, and in the red region, limit cycle is stable. Okay. However, any model of the real-world system has some uncertainty. And in the conventional bifurcation analysis, we cannot treat this uncertainty. On the other hand, robust control can analyze the influence of this kind of uncertainty. So then we combine the bifurcation theory with the robust control, and when the target system has some uncertainty measured by some normal like H infinity, then in this case, without uncertainty, bifurcation set is one-dimensional. But if there is uncertainty, bifurcation set expand to the white region. In other words, in blue region, we can guarantee the stability of equilibrium even if the system has uncertainty. And in red region, we can also guarantee the stable limit cycle even if the system has uncertainty. So then in such a way, we can extend the concept of the methodology of the dynamical system theory to the real-world system by combining the control theory. And this is an example of the complex system. Left one is the economic system, and the right one is the power system. And both has an equilibrium point. But the problem here is that equilibrium point is fully stable or unstable or much fluctuations. Okay? And I think that Dr. Mandelbrot was the first person to recognize that this equilibrium point is not so much stable. In 1960s, he analyzed the price of the cotton, and he found that the fluctuation is very large, and the distribution had a long tail. Okay? And now that field is called econophysics. Okay? And the right-hand side is the electrical power system. This is the property of load, and this is the property of generator, and there is the equilibrium point. And usually that frequency is stable at 50 Hz or 60 Hz. But we have been doubting that power system is not so much stable. But until recently, we cannot check that because that real data of the frequency of the power system were not open. But now the area or age of the power big data, so then that we can get the real data. Then we analyze the property. And this is an example of the time series of the frequency in the largest power grid in Europe. Okay? So then that the time series includes high fluctuations. Okay? And this is a histogram. So average is 50 Hz. And this orange curve corresponds to the Gaussian distribution. So then the distribution of the frequency of a power grid also long tail. And we analyze this property considering the mathematical model of the power grid composed of the swing equations. And we have found that Levy stable distribution and Q Gaussian distribution can fit the distribution of the frequency in many power grids over the world. So then in this talk, I pay much attention on the fluctuations of the complex systems. Okay. And the complex systems are generally high dimensional. So then there exist high dimensional variables, and we can get high dimensional observables. Then harnessing of this high dimensionality is quite important for analysis of complex systems. And we have been studying these topics recently, and today I talk the first two topics. Okay. First one is the modeling and prediction of big data or spatiotemporal data. And analysis of this field is based upon the so-called embeddology, well known now, and that use the delay coordinate. Okay. And second prove that if the dimension n of the reconstruction is an integer more than or equal to twice n plus 1, then the so-called delay coordinate defined by this equation. So then that the dynamics is in this case discrete time. So then the x change to fx and x to x so on, and the g is the observation function. So then that we observe through the function g. Then that this delay coordinate define the map from original state space to the n-dimensional space. And this map is generically embedding. And this theorem was extended by Samuel Otto and Jimmy Oak in 1991 for the case of the fractal in dissipative systems. So then that when the dimension of the attractile, box counting dimension of the attractile is d naught, then the integer greater than twice d naught is good enough for one-to-one relation and embedding of the smooth manifold. And this is a demonstration. So rest of chaos. And if we observe only the x variable, we can reconstruct the maybe band structure of the rest of chaos using the delayed coordinate. Okay. But recently, thanks to the development of sensors and IoT technologies, we can observe the many variables simultaneously. So then, in that case, we can use pointedly emitting like theorems, okay, by simultaneous observations. Okay. Either one and fractal case. And we can also use embedding with a mixed type. So then that's many variables and also delays for each variable. So then the similar embedding theorem hold with multiple time series and lags. Okay, so now we can use many kinds of the embedding technology to study the high dimensional time series data. So then that the delay coordinate is now like that. We can use a different observation, okay, and the different delays. So then using these different kind of embedding, we can get the prediction from each embedding. Then combining these prediction values, we can improve the accuracy of the prediction, and this weight can be studied from the many viewpoints. Okay. There are many methods to determine this weight. Okay. And this is an example of our recent application. And recently, due to the increase of the heavy rains, even in Japan, the floods of the rivers are ubiquitous. So then that we apply our method to focus the flood of rivers. And red curve shows forecast, and black dot is the real value. So then that performance is not so bad. This is 24 hours ahead for forecast. And until recently, this kind of forecasting of the flood was based upon the mathematical model of the big rivers. So researchers made models of big rivers and used those models for forecasting. But recently, even the small rivers flood, and nobody wants to make a mathematical model for each small river. So then I changed forecasting method from the model-based approach to data-driven approach. Okay? And now our system are used more than 50 local governments and companies in Japan. So then that performance is not so bad. And I also introduced another embedding we call the randomly distributed embedding, when we can get many observables simultaneously. Okay, so this is a real attractor of the target system, and the conventional way is use a delay coordinate to reconstruct the delay attractors. On the other hand, if we can get enough number of observables, then we can reconstruct the attractor or embedding without the delays. That we call non-delay attractors. And both non-delay attractor and the delay attractor are embedding of the original attractor. So there should be one-to-one relationship from non-delay attractor to delay attractor. Okay? So that observing the many variables simultaneously, we can use the information of these multiple observations to the prediction of the target variable. And we use the non-delay reconstruction for here and the delay reconstruction here. And it should be noted that the delay coordinate include the future values. Therefore, we can use this method for prediction. And to approximate this transformation from non-delay attractor to delay attractor, now the deep neural network and also the extreme machine that work very well. So then we confirm that we can use the neural network to make some transformation from the spatial variables to the time series of the target variables. So then, if we observe the many variables, then that randomly choosing the variables, we can make the many non-delay attractors. And each non-delay attractor generates the prediction. Therefore, we can get the distribution of the prediction. Then that this improves the accuracy of the prediction very well. Okay. And this is an example of the application. Top one is expression of the several genes. Okay. And the middle one is the wind speed of the wind farm in Japan. So then that the performance is very well. So then now we can use transformation from non-delay attractor to the delay attractor for prediction. That is the first topics. And in the other next topics, I'd like to talk about the early warning signals of the transition. And this research is supported by the Japanese government flagship project called the Moonshot. And my project is included in GoTo, and GoTo is targeting realization of ultra early disease prediction and intervention by 2050, very far. Okay. And using the body monitoring and getting big data of the body, we'd like to realize the ultra early disease prediction and intervention. And this research has origin in China. The idea was published by this book, Yellow Emperor's Medicine. This book was published 221 BC. Okay? And it is written that the best doctors treat diseases that have not occurred. And diseases that have not occurred called mibyo in Japanese and weibin in Chinese. I don't know the name of the English, but we are calling the pre-disease state. Okay? And the inferior doctor treat the diseases that have occurred. So I'm sorry for the present doctor, they treat the diseases that have occurred. Okay, and the concept was proposed in this book, but that is qualitative concept. So then that we are now trying to make this qualitative concept to quantitative science. That is our research. And first point is the definition of the pre-disease state. And many researchers define the pre-disease state in their own way. So anyway, that pre-disease state exists between the healthy state and the disease state. But we cannot point where it is. So then we started the definition. And we started the bifurcation in this transition. Then by using this definition, we can pinpoint the pre-disease state along the time axis. Okay, we start from this definition. Okay, this is a schematic diagram. There are two saddle node bifurcation points, and that attractor is the desirable state, and in our case, healthy state. Okay, and the blue attractors are undesirable state, in our case, disease state. And this is a tipping point or bifurcation point, a transition from healthy state to disease state. So then that we are trying to get the early warning signals of this tipping point and start very early treatment before becoming a disease. Okay? For that purpose, we propose a time series analysis method called DNB, dynamical network biomarker. And the idea is like that. We assume healthy state is attractor, and also the serious disease state is also attractor. That is why that treatment of the serious disease is difficult, because it is attractor. Okay? And by assuming these two attractors, the onset of disease can be interpreted as a bifurcation from healthy state to disease state through the pre-disease state. And there are many researches on the biomarkers, but many conventional biomarkers is static scale to distinguish between healthy state and disease state. But our DNB pay much attention on fluctuation to distinguish between the healthy and the pre-disease states. Okay? That is the difference. Thinking that they are healthy, so they never go to hospital at pre-disease state. Then we need some biomarkers to detect this pre-disease state. And the detection is not so difficult because fluctuation properties are entirely different. So then at the stable healthy state, if it is perturbed, fluctuation is small and usually fast. But at pre-disease states, fluctuations become slower and larger. And it is well known in the case of one-dimensional time series data as a critical slowing down. So then at critical state, fluctuation become larger and slower, and the autocorrelation become larger. And if we perturb a little bit, then the returning becomes slow and slow. That is a reason that it is called critical slowing down. And this is a saddle node application version, but we can also critical slowing down for hop application. And this is the data which I got by myself 45 years ago when I was a graduate student and collaborated with the late Professor Gen Matsumoto. And this is a hop application point of the switch and action, and I perturbed by the small current, and we observe with critical slowing down. So anyway, for the case of the dimension 1 local bifurcations, we can derive this kind of the critical slowing down and early warning signals. So for continuous time dynamical system, saddle node and hop bifurcation, and discrete time dynamical system, saddle node period doubling, and the minimal shortcut bifurcation. So then before transition from healthy state to disease state, there exists fluctuation, large fluctuation. Then by detecting this, we can diagnose the pre-disease state. Okay? And actually, we can show that for any pair of the DNB element xi, xj, Pearson correlation coefficient converges to +1 or -1 when the system approaches the bifurcation point, tipping point. And the standard deviation of fluctuation diverge under the linear approximation. So then as a DNB index, for example, we define I by the SDD times PCC. SD is average of the standard deviation of the DNB element, and the PCC is average of absolute value of the PCC among the pair of the DNB element. And further, we confirm the property by mathematical model of the genetic network composed of 5 genes. Okay? In this case, DNB is G1, G2, and at healthy state, fluctuation of all the genes are small, but at pre-disease state, fluctuation of the DNB element G1, G2 become larger, and in this case, correlation is -1, antiphase. And this is the property of the index. This is a bifurcation point corresponding to disease onset. That at the healthy state, the index is small, but when we are approaching the disease onset, index increases rapidly. So then we can detect the imminent disease before becoming disease by using this index. And we confirmed that by real experiment using the metabolic syndrome mice. And these mice become metabolic syndrome at the age of 8 weeks after the birth. Okay? However, we can detect the large fluctuation at the age of 5 weeks. So then that the 5th week should be the pre-disease state. And we also confirm the possibility of treatment. There is a traditional Japanese medicine called BTS, and if we can give this medicine to these mice, then we can prevent the metabolic syndrome. In that case, the fluctuation that the pre-disease state disappear. Okay, so then this is the preliminary result about POC of the detection and intervention of the pre-disease state. And we are now more sophisticated control method.
So இதோட யூஸ்வலாக வந்து இந்த டி வந்து வெக்டர் பட் டி இசட் டைரக்ஷனில் மட்டும்தான் கன்சிடர் பண்ணிட்டாங்க சார். மீது ரெண்டும் ஜீரோ வச்சுட்டாங்க சார். ஸோ இதோட எக்ஸ்பென்ஷன் வந்து இந்த மாதிரி இருக்குது. ஸோ இதை ஹாமில்டன் யூனிவர்சிட்டி சொன்னால் இந்த மாதிரி இருக்குது. நம்ம வந்து இதெல்லாம் வந்து எக்ஸ்.
Please hold on. Okay. There seems to be a parallel speaker.
Okay, thank you very much. Yeah. So that pre-disease state, we would like to move the bifurcating eigenvalue to the stable side. Okay? So then we derive the spin to control. And this is the bifurcating eigenvalue. And we'd like to move this eigenvalue by the input, feedback input. And VDI is the ith element of the right eigenvectors corresponding to the bifurcating eigenvalue. And the WDI is the left eigenvector and of the bifurcating eigenvalues. So that we can now considering to estimate these eigenvectors from the data. And we also applied our method to the brain, to the transition from normal brain to impaired brain. And this is collaboration with Dr. Kyoto Kasaya's IRCN of the U Tokyo, and we studied the schizophrenia. And there is a state called ultra high risk or at risk mental state between the healthy condition and the first episode of schizophrenia. It's the first stage of the schizophrenia. And first we thought this is a tipping point. And we applied our method. And we have found that fluctuation is largest at healthy condition. So, and if the people become the early stage of a mental disease, then the fluctuation is reduced, more stabilized. So then that we have recognized that healthy brain is working at the critical state by itself. So then that we need some extension of the data analysis. Then that we check the transitive dynamics of the healthy and the disease brain using the so-called energy landscape analysis. And this is a comparison of the typically developed people and the autism people. And there are two major states. This is the analysis of the resting state functional MRI data. And the transition between two major states is through the intermediate state for the typically developed case. But the autism case, a direct transition between the two major states are frequently observed. So we paid attention to the fluctuation, but for the case of the mixed data, conventional data analysis of average is also quite important. I saw only one example. And Dr. Okada
Dr. Aihara?
Data of the COVID-19 patient, more than 2,000 Japanese patients, and he discovered that suppressed DOC2 expression is associated with a severe COVID-19 in younger Japanese patients. So then that suppression of the DOCK2 gene is quite essential for the severe COVID-19 in younger Japanese patients. So then that both average and the fluctuation are important. Right?
Dr. Aihara?
Okay.
Yeah.
I should conclude.
Sure, please.
I explained the modeling and prediction of big data through delayed embedding and non-delayed embedding. And second, detection of early warning signal of state transition from healthy state to disease state by DMV, and its confirmation with real data of the metabolic syndrome mice. And these are my collaborators and friends. Yes, thank you for your attention.
Thank you for the excellent overview on a very exciting and contemporary topic, Dr. Aihara. Let me take this opportunity to thank the speaker once again. Thank you. Thank you very much.
Thank you very much.
Yeah. Please stay back online if possible.